Okay, in this short recording, I would like to talk a little bit about this toy here that's called the Newton's Cradle. It's called other names as well. But what you have several kind of balls that are hanging through strings and touching each other. And you pull one of them out, let it go, and then what's going to happen, the ball that's the furthest away of it is going to move out with the same height, and then it's going to keep going through a back and forth motion. If you pull two of them, you get two of them back out. This here, a Newton's Cradle that's a little bit larger than the ones that you usually buy. Okay, look at that. Okay, so you start with one, and you get one moving out. Now, in 1 second, he's going to do two of them. Actually, three of them, I think he does. Okay, and you have three out. What's the idea here? You start with one. What you are doing, you are giving it potential energy, gravitational potential energy. So as it moves down, it's going to convert that gravitational potential energy into kinetic energy. The minute it is straight down at the lowest position, all of its energy is kinetic energy. It has kinetic energy, it has momentum. It's going to collide, conservation of momentum. Now, even though the balls are touching each other, essentially we have one collision happening there, and a very short time later, a collision with the next ball, a collision with the next ball. So we have many collisions. 1, 2, 3, 4, 5, 6. Now, in every collision, we are going to have conservation momentum. Now, since they are the same masses, when one is going to hit, mv, if it's going to stop, the other one is going to have an equal amount of momentum, so it's going to move off with the same momentum. Collide with the other one with the same momentum, so it's going to give off its momentum to the other one, and you continue to have the transfer till the last one gets that momentum mv. Now, having that momentum mv means that it's going to have a kinetic energy as well. That kinetic energy is going to be converted back into gravitational potential energy as it swings up. And then the process is going to repeat the opposite way, that gravitational potential energy is going to change into kinetic energy, and so on. Okay, the point I would like to make here, despite these banging noises, what if we pull 2 or 3 balls? What's going to happen? We are going to start up with 3 times the amount of gravitational potential energy. Since I have 3 masses, 3 times the mass is 3 times the gravitational potential energy. So meaning that I'm going to end up with 3 times the amount of kinetic energy at the bottom, because of conservation of energy, mechanical energy. So I'm going to have the momentum. But then the momentum is going to be 3 times the mass times the velocities. Now, as they collide, we should have the same amount of momentum out. Now, same amount of momentum, 3 times 3 of the masses moving off with the same velocity. That's 3 times the momentum. One might ask, why wouldn't I get just one mass, the one at the end, to move off with 3 times the speed? That will still conserve momentum. 3 times the speed times 1 mass is the same as 3 times the mass times 1 speed. The problem, if you have 3 times the speed, you are not going to have conservation of kinetic energy anymore. Because, remember, kinetic energy given by 1/2 of mv squared. So if I do 3 times the speed, I'm going to have 3 squared. That's 9 times the kinetic energy, not 3 times the kinetic energy. And that cannot happen, so that's why it does not happen, and we have only 3 of the balls moving out.